Hello, I'm Giuseppe. I'm a postdoc here at the RIT, and I'm going to give a tutorial on Canuda. And this also means we are having a break from GR-MHD stuff. And this will be a hybrid, say, talk tutorial, because I don't expect many people to know about Canuda, so I just wanted to give a brief introduction. And I've created a repository for where you can find my slides, the notebook, and some data and parameter files we are going to take a look at. And it's the notebook is already should be already on the tutorial server. So if anyone wants to run it while I will go through, you can do it. And that's it. So let me just start my slides. No, like this. Okay, so let me just mention that this is not the first time we give a Canuda tutorial. So this has been a joint effort with Chen-Xin, who is here, and Elvi, who is one of the module leaders for Canuda. And what I'm showing you here is another powerful example of how you should use Coibit for doing your plots. So here I'm just showing on the left as an equatorial slice with Psi4 from a numerical relativity simulation involving also a binary black hole, and on the right you have a scalar field that we will define later. And so let me go now and describe what Canuda is. So this slide is kind of a mess because I try to put all examples from different people that worked on the Canuda suite. So Canuda is defined as a numerical relativity code for fundamental physics, where for fundamental physics we mean going beyond the GR vacuum case, and not with baryonic matter, but with some kind of exotic matter which is not in the standard model of particle physics, or attempts, if you want to try to add degrees of freedom, especially scalars, in on the left-hand side of Einstein's equations, if you want. So it's open source. It's stored on Bitbucket, that link. And we also have a YouTube channel if you want to watch some visualization of some results coming from many different people. And it comes, some of the codes are come with the Einstein Toolkit release. Some are not, but they are completely compatible. So if you're interested in doing something, you can just download them and add them to your torn list, and will be very smooth to compile and run. Okay, so we have several arrangements. We have our own GR evolution arrangement, which is a rewriting of the original link code by Ulis Perake. And it comes with the Einstein Toolkit. And now Chen-Xin, Alex, and Roland are working on porting this to CarpetX infrastructure. Of course, you start from the GR evolution, then maybe we move to other things. And at the moment, the public version of Lean reaches 6th order finite difference, and it's also it can run on Cartesian grids, but it's also compatible with YAMA if you want to use a multi-patch infrastructure. And that's it. That's standard GR spacetime solver. And then we have other two arrangements that come with the Einstein Toolkit, which are the scalar arrangement and the Proca arrangement, which take care respectively of writing grid functions, evolve them in the case of a spin 0 field, so a scalar field, and a spin 1 field, which is known as a Proca field. today we will mostly focus on scalar because it's the easiest one to deal with. But you will see, I mean, I can tell you that the anatomy of these terms, of these arrangements, sorry, are the same also for Proca and the other ones I'm going to describe now. And both scalar and Proca are simply fields that are added to your GR background. There's no, there's no modification of the gravitational theory in these arrangements. Then we have other arrangements which are mostly focused on extensions of general relativity, which I listed here. We have Canuda EDGB, which stands for Canuda Einstein Dilaton Gauss-Bonnet decoupling. That means so it's basically I think all three terms, Alex or Chloe, correct me if I'm wrong, all three terms are in the decoupling limit, right? Yes. Okay. This means that there's not really GR modification, but there is a perturbative expansion such that you can evolve these fields, the equation of these fields with some curvature correction that can come from the Gauss-Bonnet invariant, in the case of the Einstein-Dilaton Gauss-Bonnet theory, or from the Chern-Simons invariant. So if you have dynamical Chern-Simons, and Axie-Dilaton, I think, is a mixture of Chern-Simons and Gauss-Bonnet Dilaton. Yeah, okay. So here I just, let me mention that all the authors, all the contributors to the code are listed up there, and I try to do my best to take scientific results out of from everyone. So at least one of the authors is in this picture. And let me start from the picture on the left here. Can you see my, yes. So here, this is, this plot has been obtained using the Canuda EDGB decoupling. And it's basically a black hole binary in vacuum. And then the scalar field describing the new degree of freedom introduced is evolved on this background without coupling the metric. So you have G mu equals 0 and a scalar field evolution equations with a curvature term described by the Gauss-Bonnet invariant. I know this is a lot of information. There are a lot of modified gravity theories, so I don't expect you you kind of follow that that in the details. But the interesting thing here is that you can see that, so what it's plot in the left bottom plot is basically it's not equatorial, but it's the XZ plane, in which the contour lines are this Gauss-Bonnet invariant. And as you can see, it's white at T equal 796 m, which means that there's no scalar field there. So scalar field is 0, but at some point where the near merger, there is this sudden growth of the scalar field, and this phenomenon is called dynamical scalarization. It's spin induced because it's the spin that induces that, but it's called scalarization. So the sudden growth of this field is caused by the fact that the Gauss-Bonnet invariant in those red contour lines are sourcing the field to grow, and the growth is very rapid. Then we have massive hair in DCS gravity. If you want to hear more about that, both Chloe and Alex are here. So if you want, you can ask them. But basically, if I understand this correctly, on the left, you have the evolution of this scalar field in normal GR, while on the right, you have the same thing, but it's evolved in with the DCS invariant. And you can see that the profiles are quite different. So the evolution of the field is affected from the fact that it is in a different theory of gravity. And this ends the modified gravity plots I'm showing you. And you can also do other stuff like multi-field boson stars, if you're interested in that. And this is a combination of how both the scalar and Proca terms can work together at the same time. And then I wanted also to put this plot here with kicks in charged black hole binaries. can actually, you can have kicks depending, the kick after merger can depend on this lambda2 coefficient here, which is basically the charge to mass, it's the charge to mass ratio, but it's the charge that these black holes carry. And this is GR, this is just Einstein plus Maxwell, so it's GR plus the Broca evolution arrangement. And then you have some more standard thing if you want. The one I'm working on, so binary black holes in scalar clouds, which we will focus on today, so I'm not going into much detail now. And then in my case, it's in full back reaction. So we back react the scalar field on the metric, while this black hole binary is in light fields, gravitational molecules. It's kind of the same setup, but without back reaction. I'm going to discuss in the tutorial where we are running an example that can be thought as the single black hole equivalent of this binary case. Okay, so let's focus on the scalar field. I put the most generical action for a scalar field minimally coupled to gravity. We also have the cosmological constant, but that's there just for flavor. We're going to set it to 0. And in principle, you can have a generic potential for the scalar field. In the scalar Thorne, you have a choice. It's a very specific potential. But the standard choice, at least I work with, is the massive scalar field 1. So the potential is just given by a mass term and a self-interaction square, the standard one. And the equation the scalar Thorne solves, if you want, is Klein-Gordon that can be modified with any potential you want. There are, as I said, there is the massive potential is already there. There's another choice, but it's some self-interaction with some higher power. But it's very easy to add another potential if you're interested. I don't know. Usually in field theory, when you have a scalar field, you can also have a lambda phi to the 4th. It's easy to add. It's not really hard to add. So yeah, I just use this slide so you can understand what kind of equations I'm going to solve. And just to describe the anatomy of one of the, I'm using the scalar arrangement here, but the Broca and the modified gravity ones are probably the same in the sense that you will always have, in total analogy to how you have it in the Einstein toolkit, you have a base Thorne where you divide your green functions. Then you have an evolved Thorne where you put the computation of your right-hand sides. And then you can have different initial data Thornes depending on what you want. So for instance, in the scalar base Thorne, we define the grid functions, which are, of course, the scalar Thorne is for a complex field. But if you are interested in a real one, we just set the imaginary part to 0. But the grid functions are defined for the real and the imaginary part of the scalar field. And since Klein-Gordon is second order time, you need to redefine your system of equations as a first order in time. Then you define your momentum, which is the time derivative of the scalar field. And that's another grid function we set. We also define parameters that are going to be used from the other Thornes. It's better to define them in base, so they won't be specific to a Thorne, but they will be defined such that all the Thornes can share it. And for instance, you can have, as you will see in the parameter file, the scalar field mass. You can have your coefficients if you add potentials. You can also set the evolution method. We have our own, but if you have your own, you have your own Klein-Gordon solver, you can just use that and define the grid functions using scalar base. There's nothing wrong with that. Then let me talk about scalar evolve, which implements the scalar field evolution equations. At the time being, the one you can find within the Einstein toolkit has fourth order finite difference. Can run on Cartesian grids and also multiplatch. Behind the scenes, we are working on higher order finite difference to add. And I mean, the evolution equations part is kind of the same you have also for the gravity part. I would say when you have math help, you also need a routine to compute the energy momentum tensor you want to study if you want to input in the metric evolution, but this is interesting also if you don't back react on the metric. In that case, it's more like analysis tool. Yeah, then you can set boundary conditions in the same. Yeah, on a Cartesian grid is in the same way. Also for multiplatch is the same way you do it for standard Einstein toolkit terms. Use method of line, so it can interact with the mole thorn. And fourth, I mean, we use the Einstein toolkit one, so that was was kind of more than that. Okay, so these are I would say the core modules of the scalar arrangement. Then we have several choices for how to set the initial data. For instance, if we want only to study how the scalar field evolves in a curved background, we can use scalar init, which has several profiles you can choose from. There are Gaussians, radial Gaussians. You can add some angular dependence with some multiples definition, but it's up to you what you want to study. An interesting physical thing is to study quasi-bound state solutions for massive scalar fields, which are solutions for the Klein-Gordon, for the massive Klein-Gordon equation around a rotating black hole. Recently, they have been studied intensively due to the so-called super radiant instability, which is basically when you have a scalar field around a rotating black hole, there is an instability you can trigger, so your scalar field can grow macroscopically at the expenses of the energy and angular momentum of your black hole. So the black hole will spin down and field will grow. And this is something we are going to run a parameter file on in the tutorial. And yeah, we implement the full numerical solution that was worked out by Sean Dolan in 2007. And that's it. I don't know how many of you know what a quasi-bound state is. Okay, so bound state, yes, the hydrogen atom, okay? Quasi is because the solution looks very similar to the hydrogen atom. So you have some frequencies at which the field can oscillate. It's quasi because you have a black hole, so you have an horizon. It will dissipate your field. So the eigenfrequencies you want are complex. So you have an imaginary part, and that's it. That's the quasi comes from the dissipation of the black hole. And then we also have a modified version of the two-puncture storm in order to solve coupled initial data for a binary black hole and scalar field. And you need to, I mean, we didn't add this to, in two-punctures itself has also an option to switch on some energy density from a TOB star, I think. But the thing is that since the stress energy tensor of the scalar field has different weights inside, because you have derivatives and you have the field, and that is a bit of a mess when you want to solve an elliptic equation, because you need to, I mean, there are different ways to do it, but it's not as easy as a perfect fluid neutron star. Okay, so this takes care of that. And if you want to study problems with back reaction, now you can do it consistently. And this code is available with the latest release of the toolkit. And I think for describing things, I think I'm done. The only thing I wanted to mention is that in the Procathon, you can find another 2 punctures, but it's called kerproca. And it doesn't work for binaries, it only works for single highly spinning black holes. So if you see that, I mean, if you're interested and you see that thorn in the Proca arrangement, that's not going to work for binaries. Okay, so now I'm finished with the description. We're going to run the notebook, and we are going to have 2 examples. The first one is, as I was saying, a massive scalar field quasi-bound state around the rotating black hole. And the other one is using this new code we have in the toolkit to actually generate a binary black hole system coupled to a massive scalar field.
We have a tutorial notebook already loaded on the server.
Yeah, I'm going to use that. Let's see. Yeah, so I think I see if you open the menu, it should be there. Yes, it's this one. It's tutorial ETK Canuda scalar. Just click on it.
Now, in order for that to work, you have to run the Roland's tutorial, at least
Yes.
set up styling.
Yeah. Yeah, so here there is a small introduction, which basically a very short summary of what I said, or links you can find. Yeah, I just said this. Okay, so we can start with example 1. Let me introduce it first. So what we are going to do is to evolve a massive scalar field with a mass parameter of 0.42 around a black hole with dimensional spin of, so a highly spinning black hole near X1. Okay. As I was saying, this is interesting. This case is interesting if you have a quasi-bound state, because it can actually grow macroscopically when thanks to the superradiance stability, it needs to satisfy the superradiance condition. And this means physically that your scalar field, your azimuthal number of the scalar field, in completely analogy with the hydrogen atom. So you have 3 quantum numbers, NL and M. So it needs to have some angular momentum, and it needs to correlate with a black hole. So if you satisfy that condition, you can actually trigger the instability and extract energy and angular momentum. And now you can ask, why is this interesting? The fact is that after you grow, since you are considering, I didn't say it, but we are considering here a real scalar field. This can actually, for the Neuer theorems of GR, after this field grows, it cannot stay there forever, because this is not a real hair. So it needs to dissipate somehow. And if you do the math of this, you will actually see that this thing, the scalar cloud, will emit gravitational waves at some point. There are, at the moment, currently people trying to study that. But yeah, I mean, we have everything we need in the toolkit besides besides this kerr quasi-isotropic Thor, which is part of Canuda but not in the Einstein toolkit. For some reason, it's in the repository, so you can just modify the Thorn list, and you can download it. And yeah, I mean, if you want to have a very short description of what this Thorn does, is to provide analytical initial data for carrying quasi-isotropic coordinates, where this coordinate is defined here. And that's mean, without that going into any detail, is more well suited for numerical implementations rather than Boyer Lindquist, for instance. Okay, so I'll just run the usual magic thing. Then Steve added this magic to add the new thorn in the thorn list without opening the file. So you can just run it. And this will modify the thorn list and add the thorn we need. And then we can just download the thorn list using get components. You can see it actually downloaded something, so the thorn list was successfully modified. And then we can go into Cactus and we rebuild. I expect this will take nothing to do, since it's just one small. Oh, it didn't modify. Okay, it's there. Ah, no, yeah.
Yeah, you forgot to run the checkout part. No. Scroll up. No. Move your arrow. Yeah, just there you go. No, scroll up more. Okay. What's your username?
GXFSMA. Probably I'm reading the wrong thorn list.
Scroll up a little bit. No.
In the notebook.
The notebook. Stop. Okay, so that get components code does CD dot C until the slash.
Sorry, can you repeat?
No, I was just reading it. Don't see why that's not working.
I tested this morning, will work.
Yeah, maybe it's a duplicate form.
It's not finding.
It's not finding it. So that's why I'm saying probably it's reading the wrong thorn list.
Just so I can see the next commands.
Oh, maybe. No.
We're doing our last off text as a range just to see if there's anything there. Maybe it's just the.
I am confused. I mean, that is definitely in your thorn list. And could you run the get components line again?
Was it built already and it needs a replay?
Oh, wait.
It says it's checking it out. Then there's the default is fully link. So yeah, that's probably what it is. Okay, let me see if I can delete it for you. Just leave.
Yes.
That's capital.
Okay, try rerunning. Just rerun the
And it doesn't have it.
Yeah, it's not in there.
rerun the get components thing. I just deleted the link. Okay.
Do it again.
Okay, run that same cell again.
Okay, it's there.
Well, yeah.
Should work now.
It should have, but I wanted him to run that other cell, but whatever.
He just did it before.
No, but I mean.
Now it's no, probably there's no reference for this.
He was wanting to see if you ran get checkout again, if they would try to check it out again.
Yes.
That was what it was. Oh, okay.
Yeah, it's not in the repos though.
Yes, it's building the link incorrectly.
Oh, add a minus L to your last line. The first one, make sure that the link is actually correct.
It says it's a dead link. This is so crazy.
But does it work for anyone else? Or is it just me?
Does it work for, does anyone else have this problem?
You're not,
Speaker only problem.
what directory are you in when you run the cell at the bottom? Because you're not in the CD cactus anymore. You have to remove the auto scroll problem. Does it?
Oh.
Yeah, I'm in Cactus.
I think I might know the problem. Hold on.
I mean, if it works for you, we can go ahead. Oh, it works for people online too.
Could you please run your checkout script one more time?
Yes.
What if he runs with that update?
Oh, what happened?
Okay, now try running it. Try running that checkout script just one more time. See if it does anything. There you go.
Okay, now it should work, yeah. And let's run this again, just for,
Wait, somehow or other you had deleted the actual thorn from your repository. I don't know how you did it, but
I have no idea. Okay, it worked. Yeah, let's wait this to finish for me. Let's wait for the sim factory stuff to be done.
But like, we have this really ID. And people really. Really? Oh, we gotta go down. Yeah.
Okay. So now we can, you could already done it, but I could. Now we can run together the first example. So we just go back to the home directory. Okay. I mean, I don't expect you to have, we can create a folder to store the parameter files we're going to write from the notebook. So I just run this mkdir par Canuda. And we're going to have a look at the parameter file. As Leo explained yesterday, you always have to start from someone else's parameter file to set up yours. And probably in this one and also in the second one, there will be some stuff that you actually don't need it, but at least this works. So I'll just highlight the features from Canuda. So we have the thorn we just downloaded, which is care quasi-isotropic. And then we have these three calls here, which are scalar base, scalar evolve, and scalar init, which I described before. just the base storm, the evolution, and in this case, since we will not back react on the metric, I set up the quasi-bound state using scalar init. Since this has to run on the tutorial server, is low resolution, smallest possible grid, so we don't mess up anything. And how you can understand this is low resolution? I mean, there is a small grid, and then we set 5 refinement levels, which are, this is very coarse resolution. And yeah, I'm actually setting up some refinement levels because we have a black hole, and we want to be sufficiently, we want to have sufficiently high enough resolution to describe it. This parameter file won't have it because it's, as I said, very low resolution. But if you on Bitbucket, I also have the production run version of this parameter file. If you want to have a look at that, which is actually very small changes from this one. It's just setting up the refinement levels better and enlarge the grid, so you avoid reflection from the boundary or whatever, and setting up some extraction radius that I will describe. Now we go in the section where you actually find Canuda parameters. So in order to set up this scale quasi-isotropic term for the metric, you need to add these keywords to initial data, initial lapse, and initial shift, which will set up the analytical expressions for a curve black hole in quasi-isotropic coordinates for you. And then we can actually go here where we set the parameters we are interested in. So in this case, we have it's, of course, it's a single black hole with mass. This is the horizon mass of your black hole, and it's the ideal mass since there was only one. And this pos plus 0 defines the x component of where you want to put your black hole. If you want to put it at plus 16, you can do it. Here I'm just putting it at 0, but as also Lee explained yesterday, you don't want stuff exactly on a grid point or in 0, so I just set it up a bit to the right, 10 to the minus 4 to the right. Then we have the spin. As I said, we're gonna set this to 0.99, and then you have this epsilon r, which is actually, I couldn't have put it because this is by default this value, but this is actually just it's just a floor value for when you are because you are computing. So when you set up initial data, you run the same formulas all over the grid. There can be a point in which the distance between your point and the black hole is very small. So if you have terms like 1/r, this can blow up your initial data. So this is just a floor value, like if the distance between the point I'm looping on and the point where the black hole is less than 10 to the minus 6, just use 10 to the minus 6. So terms like 1/r don't go bad. Okay, this ends the initial data for the metric side. Then we have the calls to the scalar form, the scalar arrangement. We have 2 parameters from scalar base. The first one is a keyword that actually tells what kind of initial profile do I want for my field. So in this case, this is the keyword for a bound state. But here you can have a Gaussian and can be EDSF Gaussian, just like that. And there are other profiles which are superpositions of Gaussians. So there are many things you can do. If you want to know more about that, you have to go into the param.ccl of scalar base. And then we set the mass. They set 0.42. Why? Because it's the most efficient one for spin 0.99. And then, okay, this is something this could improve, I think. What's the point here? The point is that you can set up the quasi-bound states if you want, even without Kerr quasi-isotropic, because they don't talk to each other. The thing is, you need to, if you want to evolve in a Kerr background, you need to set up also the initial data for the metric. So that's why there are some repeated parameters. Okay. Yeah, one good way of doing this probably is to share the parameter between the two terms. But then if you want to use another initial data term, you cannot do it because you need to inherit, you need to put it in your term list and stuff like that. So the easiest thing, actually, that's probably why Kerr quasi-isotropic is not in the toolkit. Think about it. But yeah, I mean, this M plus, post plus, and spin plus needs to be the same you set up in Kerr quasi-isotropic. Otherwise, you will not study the system we want to. And then you have these parameters omega r and omega I. As I was saying, these quasi-bound states have a specific eigenfrequency, which has a real and an imaginary part. We just took this from Sands-Dolan's paper, where you can find some examples, and some is just an upper limit because the quasi-bound states are described by an infinite sum of stuff. So that's like the upper limit the code does. Okay, so this ends the initial data part. Okay, for the evolution, which is something you don't usually see, since the Einstein toolkit is for binary black holes, so you have dynamical spacetimes. So most of the time people do dynamical backgrounds, but you can actually, if you don't want to evolve the metric, you can do it. You just set static to all those options as in the parameter file. And another thing you have to do is to stop the prolongation among the refinement levels, because you don't need it. The grid won't regrid. The metric is not evolving. One warning I can give you that comes from my experience is that I mean, for testing the code for the scalar field, you usually run this kind of parameter files to see if you mess up the code or not. So you don't evolve the metric, you only evolve the scalar field. And then after you tested it, you want to move to a dynamical background. You have always to remember to remove those non-lines, because otherwise you won't understand why your code is blowing up, and it will save you much more mental health than I was not able to. Okay, then we have the choice for what kind of evolution term you want to use for the scalar field. As I said before, we provide our own, but if you're your own one, you can just add a keyword that points to scalar base, and you can use your own. So in this case, we are using scalar evolve. So I just said scalar evolve, and the sky floor is the floor value of the conformal factor that is used in the routine that compute the right hand side. Again, this is again just to avoid large values for functions that involve one over conformal factor. Let me see. Okay, since I'm only evolving the scalar field, I'm applying the dissipation only on the variables I'm interested in. And the code is fourth order, so the dissipation goes to fifth. It's a standard choice. You just need to remember if you want to switch between finite difference orders to update this, because I mean, if you're using the dissipation term, the rule I use is one order higher with respect to your finite difference order. So fourth order dissipation, fifth order, sixth order finite difference for your code, seventh order for the dissipation. That's the rule. Then Runge-Kutta fourth order, standard. Leo already explained all of this stuff, so I'm skipping it. Okay, one thing we didn't see yesterday is the multiple extraction. So you can, what you can do, since I mean, the ultimate goal, if you are simulating a binary black hole, is to gain information about the gravitational waves emitted. In this case, I'm more interested in the scalar field, but it's the same. You can use the same term to extract them, which is the multiple term, which basically takes your grid, any grid function you want to study, you put it here, and what this we're going to do is to project the grid function on a sphere centered in the origin and surface some radius that you want to set. In this case, I'm using 10 because this is, I mean, I cannot go above 10 because my grid goes to 16. That's the only reason why. And to study the field evolution, I just asked the real part of the scalar field. I want the multiple of the real part of my scalar field. And in order for this to work correctly, if your function is complex, you also need to provide you also need to provide the imaginary part for the multiple term to work, because if you don't do it, it will give you wrong answers. And SQ is just the spin weight of your grid function. I mean, if it's a scalar, it's 0, vector 1, gravitational wave is -2, because that's the convention. Okay. Non-checker just checks if your grid functions develop nonce, and it will kill your simulation if it finds it. Then we have some output, but we already see this yesterday. Checkpoint, and that's it. Yeah. So if you run this cell, it will create this parameter file in the folder we created before, and then we can check that that's actually in there. It's there. So now we would like to run it. So we go to the cactus folder, and we can use SimFactory. So this first command will create the directory tree for the output. I mean, you can do create, I mean, I'm doing it separately, but you can do create run, and it will do it automatically. In this case, it creates submit because we have Slurp. Okay. And this is very fast, so it probably just finished. If I run this again. Oh no, probably because we are all running. It's not done yet. So we can have a look at the output. Okay, job already complete. Okay, so I mean, you can run it, but the output will be probably nonsense because the resolution is low. So what I did is to prepare some data. We can do some plots to see what I usually look at to, I mean, I use this stuff to debug, but 10 years ago, this was like state-of-the-art research, like single black holes around the rotating black, scalar fields around single rotating black holes. Okay, so I'm not using Qubit for this because I was just lazy, didn't want to do it. So I'm just importing some matplotlib stuff. And something you didn't see in the previous days is this package here, which does Fourier transforms of your signals. Now, you can, if you run this cell, it will download the repository I showed before on the tutorial server, so we can actually do some plots. And yeah, I also have an LS that tells me what's actually inside the folder we're looking at. We have the parameter file, and we also have the one multiple of the scalar field at different extraction radii. As I said, this parameter file is a larger grid and higher resolution version of the one I showed you. The output was much larger than this, but since the other day we had the storage problem, I reduced the data set. So the only thing we can do, we can cd to the folder, and with this cell, I'm basically reading in the multiple outputs are 10 and 40M extraction radii. And then you can just run the cells and do a plot. So here on the x-axis, I have the time. And on the y-axis, I have the scalar field that is scaled by the extraction radius. And now, if you are familiar, I don't know, with plotting this stuff for gravitational waves, you know that there's a 1/r decay. So if you do this plot, the curves need to match, otherwise there's something wrong in the code. But in this case, it's okay because this is a quasi-bound state that has, would say, an exponential decay as r goes to infinity. And this is okay. This is what I would expect. And I know you're not familiar with this, but if you're interested in reading these quasi-bound state solutions, I have two links here. This one is for the first paper that actually described the solutions for a massive Klein-Gordon equation around a rotating black hole, which was by Detweiler in 1980. And that works for small mass coupling. So when basically this product m times mu, where m is the mass of your black hole and mu is the mass of the scalar field, is small, so much smaller than 1. And the other paper is Sam Dolan's paper, where the equation is solved without any assumption. And in fact, the solution is numerical. So in order to check if my scalar field evolution is okay, well, what we can do is to analyze the oscillation frequency. So what we've seen here, what's actually the frequency we are looking at. So if you use the Detweiler paper, you can get an analytical estimate, which is the one I put there. And then what I do is to just do a Fourier transform of the signal. And yeah, I'm just plotting the expectation. The peak of the Fourier transform is kind of where it should be. So this should be okay. Any questions? So I'm switching to the binary now. So wait a minute, because I can't hear. Can you say it again? I can't hear.
Yeah, it's on their side, it's not on our side.
Okay.
Either. So whoever is just speaking, we can't hear you. It's just kind of.
Yeah, you can write in the chat. I mean. Or on Slack if it's better. I don't know. Plenty of time. Okay, I'll just go forward because we're almost there. I mean, now what I'm going to do with the next example is just to set up a binary black hole coupled to a scalar field using the new code which is available in the Einstein Toolkit. And what I'm going to do is just to, for this thorn, we only have a scalar field that can be chosen as a Gaussian. Specifically, you can choose a monopole profile, so no angular dependence, so spherically symmetric. Or you can actually have a dipole, so L equal M equal 1 dependence. People have studied that this actually, I mean, the scalar field profile actually doesn't matter in binaries, because whatever the initial profile you set up for your field, I don't know, you can set up a scalar cloud around involving both of them, but as soon as the black hole starts coalescing, the scalar field will accrete very rapidly on the position of the two black holes. So you will always have some kind of individual cloud around the black hole, around each black hole. So for this, I mean, for this particular example, I'm setting a spherically symmetric Gaussian around a binary of separation 6m. So this is another test parameter file if you want. And this scalar field will cover the entire binary because its width is 10m. I forgot the m there. So it completely involves the binary. And the only warning of this parameter file is that when you have a scalar field, you also have to modify your gravitational wave extraction. Because if you compute the Weyl tensor from which psi4 is defined, there are contributions coming from the scalar field. So I'm just putting here a warning because in the Einstein Toolkit branch of Lin, where our gravitational wave extractor thorn is called MP scalars, this doesn't have back reaction terms added yet. This is something we are developing. I mean, you can always check out my branch and it's there, but it's not public. And yes, so I mean, if you run this parameter file, everything will work out okay. But if you look up psi4, that will be wrong. Just this warning. Okay, so let's see. So the thorns are the same as before, but we are switching scalar init with 2 punctures PBHSF because we change the initial data thorn. Okay. So let me, the grid is the same as before, probably. Here I have pi symmetry because it's equal mass and spherically symmetric for the scalar field. So you can add a layer of symmetry and they are not spinning. The black holes are not spinning. We have 2 centers of refinements because we have 2 black holes. And okay, we get here. So we have, if you want to initialize the metric with punctures, with BHSF, very originally, we just added that underscore BHSF to the 2 punctures keyword. And that's what tells ADM base that we are using our own initial data thorn. And most of the parameters are the same as in 2 punctures. So since nobody discussed how to set up initial data with 2 punctures, because we saw Fuka initial data, we saw NERP elliptic, and now we can talk about 2 punctures, even without the BBHSF. I will tell you which ones are from the thorn and the others are the same, basically. So this initial lapse psi exponent is also present in the original 2 punctures that basically sets the power with which you want to initialize your lapse, which is actually set up here. So it will be the conformal factor to some exponent, and the initial lapse exponent will give the actual value you're going to use for the lapse. Then this, as you might guess, this is a parameter that is only in 2 punctures PVHSF, because you can switch this to yes or no, depending or not if you want to set up back reaction in the initial conditions or not. If you set this to no, you will get the same result as 2 punctures, as it should if the code works. Then we have this delta parameter, which is linked to how we solve the initial data. Basically, as I was saying, when I showed the stress energy tensor of the scalar field, I told you that there are different contributions with different weights, if you want, because you have both field derivatives and field itself. If you put both without rescaling properly the field, the equation, the elliptic equation, so the Hamiltonian constraint, in this case, because we are adopting a 2 punctures approach, will not be well posed. So what we were getting were, in the first place, we were getting, as we increased the resolution, the code was not converging. But there was a mathematical reason. So we find out that, and if you actually rescale by some power which is less than 2.5, the code works. So we just did what you do with the metric and with the extrinsic curvature. So using conformal rescaling also for the scalar field. You can also, and if you are into this, you can also see that this is not a fixed power. This is not a fixed power because the covariant derivative of a scalar field doesn't have Christoffel symbols because it's a scalar. If you do this for a Proca field instead, you can get a natural exponent out of the way how Proca fields transform under conformal rescaling. That case, I think, is 2. I don't remember, but I mean, you have freedom in choosing it, but there is a natural choice that kills the Christoffel symbols when you do the conformal rescaling. Okay. I think, yes, all of this is in the standard 2 punctures. So you have a choice to set the bare masses of the punctures, which are not the horizon masses, but they are just normalization parameters. What you can do is to tell 2 punctures to iterate the method until the black holes you want have the mass you want. So that's what target n plus and target n minus do. So we set it to equal mass. Then you have part B, which is the semi-half distance between your black holes. So the distance is 6, so part B will be 3. And then you have the parameters for the P plus and P minus, which are the X, Y, and Z component of the momentum of your black hole, of the linear momentum of your black hole. And then S plus and S minus are the X, Y, and Z component of the dimension full spin. When you add spin, you always have to remember when using 2 punctures to multiply the dimensional spin you want times the target mass you want to achieve. Then TP epsilon and TP tiny are kind of what I explained before when I was to epsilon r. These are just floor values for the radii of the punctures or stuff like that. Then we have endpoints A, B, and phi, which are your collocation points. So these parameters basically rule the spectral resolution of two punctures, which is based on a spectral method to work. Yeah. And then again, we call scalar base because we want to put a scalar field in this initial data point, in the initial data computation. And this time, instead of using scalar init, we initialize the scalar field directly from inside the new Thorn. And in this case, we have a Gaussian. So in the initial scalar, we have SF Gaussian. And in this case, the mass is 0.4. And a single mode, because it will be, I mean, it's just a Gaussian by itself. You don't have any superposition between, you can have, if you want, superposition between different profiles. Then, as I said, it's spherically symmetric, so it's a monopole, so L and M are 0. And then this sets the amplitude of your scalar field. And then the peak position, in this case, the peak will be in between the black holes, so the cloud will contain both of them. And this is the width. 10M. One note, if you want to use this code, is that the resolution of the solver changes with the amplitude of the scalar field. So the larger the amplitude, the larger the number of collocation points you will need to achieve convergence. In this case, for instance, for 5 times 10 to the minus 3, I mean, I put 30, 30, 24, but that's actually a low resolution for this hybrid two-puncture scalar field. You need at least 80 collocation points on A and B to achieve convergence. And I mean, for the initial data, that's it. This time we are evolving the binary as well. So we're using lin for doing this. And compared to the previous parameter file, you have lin BSSMO, which is the keyword to activate the space-time solver that is, I mean, is the one in Canuda. But again, if you have your own space-time solver, you can do that. You can use that. And that's it. So we have also lin as its parameters. So we have impose conformal factor floor at initial, yes. So it will set the floor value for the conformal factor at the initial time. Eta beta is basically the coefficient you have in front of the gamma driver condition for the shift. That's the conformal factor floor value, which is one. I mean, it's the same reasoning we were doing before. So just define a conformal floor. You just define a floor value to avoid large 1 over conformal factor terms. In this case, we are running with 4th order finite difference because the scalar field, the public version of the scalar field only has 4th order. So, but for lin, you can also choose 6th order if you want. And then you can choose to calculate the constraints and to use advection stencils for the advection derivatives. Scalar evolve is the same as before. And if you want back reaction, you need to add these 2 flags here. So, which are from TMU base. So you need to set both to yes, because if you set one to yes and one to no, it will probably die because they are somehow linked in a way that I don't. Also, because this is called stress energy storage here, but in the source code, it has another name, which is set energy state or something like that. But again, if you want to run without back reaction, you just set you can take the same parameter file, you put no here and no in the back reaction of the initial data. And that's going to change it. Now the dissipation is applied to everything because we are evolving the metric too. And the rest of the parameter file is, okay, this is one thing we didn't see yesterday probably, which is the puncture tracker. So if you want to follow the tracks of as how the black holes move in the grid, you can do it with this. With that, we'll basically track how the shift vector evolves at some points on the grid. And this will also, I mean, this is something you do when you're, you're interested in the now, if you want, for instance, do eccentricity reduction, like the Einstein, there's a public toolkit available for doing that takes as input the output file that comes from the store. The eccentricity reduction is a combination of NeRPy plus for combining for computing the 3.5 PN initial parameters, and then there is a script which is not part of NeRPy, I think. No, it's not. That will compute the eccentricity reduction corrections automatically. Wave extraction is the same as before, but we added the Psi4. In Canuda, the extractor thorn is called MP scalars, as I was saying before. So we just use that. But I mean, you can use PyScal4, which is the one in the toolkit. It depends on what you want to use. H-shape funder, already explained yesterday. Let's skip it. Quasi-local measures as well. Okay, so yeah, that's just output checkpoint. Okay, so if you just run this cell, it will create. No, it doesn't, because I didn't change folder. Probably. I didn't run this. Okay, so we can run on LS. I have it here now, and we can try to run it. So again, we can create the tree directory, and then we submit the simulation. And this will take probably 10 minutes because for two punctures, we are targeting the horizon masses. So it will solve iteratively until it finds the value it wants. Now it's low resolution, so it will probably find the mass, but if you look at the constraints, it will be bad. But again, I have prepared the data. So we can have a look at what changes. I ran actually two simulations, one with back reaction and one without. So we can see how the output changes when the scalar field fits in the right-hand side of SS equations. Okay, this is just an LS to see if it's working, okay. So I'm just importing some data. So the first plot I want to show you is the L2 norm, is the reduction of the Hamiltonian constraint on the grid. Specifically, it's the norm 2 reduction. So this computes the L2 norm of the Hamiltonian constraint on the whole grid. And we can see that coupled and decoupled is back reaction on off. And we can see that there's not much difference from the standard two punctures. I mean, this is not how you should do it, because you should look at the grid function itself at the initial time. But then I had like a huge file that I didn't want to upload on Bitbucket. This basically tells you that the evolution of the Hamiltonian constraint is the same. So we achieve the same kind of the same kind of if you want, numerical error as in the vacuum case. Now we can have a look at the trajectories. These trajectories are read from the horizon finder, but you can do the same plot using the puncture tracker if you want. They are going to be most the same until near merger, because near merger you have the formation of the common horizon. So it might happen that the apparent horizon finder won't find the two black holes at that point. So if you want a complete plot up to merger, you have to use the puncture tracker. Yeah. But I mean, for the purposes of what I want to do is just to show you that the trajectories are not that different. Probably they are in the very last stage where you can see that here there is a very small deviation, but it's very small because actually this is a cumulative effect. The longer the spiral, the longer the scalar field can back react, the longer will be the detachment from the vacuum case. And we can see why is that even if it's very small in this case, what I'm doing here is to plot how much the apparent horizon area grows in time if you have the scalar field or not. So you can see that in the no back reaction case, it stays, I don't want to say constant, it stays within numerical error, I would say. But if you have the scalar field, you can see that this kind of grows in time. So you're actually feeding in, the scalar field is accreting onto the black hole, and the black hole is basically absorbing energy. And to finish, just want to show you the difference in the waveform. As I said before, this is wrong because the public version doesn't have the corrections to the scalar field. But you can also, I mean, you have to zoom in a little bit, but there is a bit of displacement here. It's a phase shift, even if we don't consider those corrections. We only have the pure back reaction effect of the scalar field here. And I think I'm done.